Hello and welcome back to another episode of Math with Stone. Today we got a good one for you. We got centripetal forces and circular motion, but with things that are vertical. So this is like a vertical loop-de-loop, so to speak, or a wheel or a tire or something where you are spinning around like this bucket is around vertically. Okay? And because it's being spun vertically, we got a lot of things to think about. We got things like gravity must be accounted for. And because gravity is happening, objects are not going to be traveling at a constant speed. At the top, you're going to be going relatively slow, but then as you go down and careen down the circle, you would speed up because of gravity, and then you would slow back down on your way back up. And then you would speed up and you would go back down on your way back up. And like constantly, it's going to be changing in speed. So at the bottom, you're going faster than at the top. Okay, so at the bottom of the circle, you would be going faster. And at the top of the circle, you would be going slower. All right? And with that in mind, there's also a few other things to think about. We would still have centripetal acceleration occurring, but that centripetal acceleration has got some other stuff happening with it as well. Okay, so gravity is always going to go down. So mg, gravity is going to go down in both cases. Gravity is going down. But centripetal acceleration is going to be pulling you inward, which is different than what I'm drawing right now. I'm drawing right now the tension, okay? The tension overall of the string, assuming that the centripetal acceleration is constant, okay? So assuming that we are accelerating around the circle consistently and whatnot. So if you think about this bucket, for example, at the top of it, is the tension going to be greater or less than it was before? So if you think of a string, like a loose string, at the top of it, when you're at the top of the circle, what would happen if you were not accelerating around the circle quick enough? Well, the string would become slack, like I kind of drew a slack string, and the bucket would literally fall on your head, okay? So that means a few things. That means that if you took the tension of this, it would be essentially equal to your centripetal acceleration force, which is mv squared divided by r, and you would be having gravity kind of fighting that and be taking away what would have been a relatively taut string. Gravity is kind of making it looser, okay, which is why we subtracted here. Versus over here, the tension of the string would actually have gravity helping it be even more taut. So I don't know if you've ridden a roller coaster lately, but at the bottom of the circle, it feels like your blood vessels are going to burst a little bit more because you have g-forces, and that is because gravity, as well as that centripetal acceleration, are both acting and causing the tension, which is u, to be pushed even further upward. All right? So the same thing could be happening here. The bucket, if you think of it down here at the bottom of it, so if we had the bucket at the bottom, if there were water in the bucket, you would not be worried about that water leaving because gravity as well as everything else happening is really, really, really kind of keeping it there. All right, keeping the tension strong. Let's do an example. All right, it has calculate the minimum tension of the bottom at the bottom of the bucket for the motion as it has a velocity of 8 meters per second at this point. At the bottom, it has a velocity of 8. I'm betting in the future when we might do one at the top. All right, so 8 meters per second at this point. The bucket has a mass of 2.5. It has a radius of 1 point. And apparently this is an 18-point question. This might have been directly from an AP exam. So with that in mind, we would have the tension. I'm doing part A right here. The tension would be equal to mv squared divided by r minus mg because it is at the bottom. We would be essentially plus mg because it is at the bottom. The answer key I had at the top, so I was getting confused. All right, so what do we got? We got a radius of 1, we can plug that in, so the tension would equal 1 for the radius, the mass is equal to 2.5, the velocity is equal to 8 squared, and then we would have to add the mass, which would be 2.5 times gravity times 10. Okay, calculator time. We got 2.5 times 8 squared plus 2.5 times 10. We get a tension of 87.5 newtons. Very nice, very nice. Okay. Then, part B. The bucket is filled with orange soda. Calculate the minimum speed of the bucket at the top of the circle in order to keep the orange soda from falling out of the bucket. Well, in order to do that, we need to figure out exactly what would happen at the top to where it would perfectly kind of like not stop. As long as this keeps going, we are going to be fine. So as long as it keeps going, we need to make sure that the tension essentially is bigger than 0 newtons when in relationship to like gravity. As long as the tension is a little bit bigger than 0 newtons, we're going to be fine. All right, so that means that the mv squared over r minus the m times g, that has to just be bigger than 0. All right, so mv squared over r, it has a mass still of 2.5. 2.5, we're looking for the velocity, right? V squared over r, the radius is still 1, minus the mass, 2.5 times 10. That has to be at least bigger than 0. Can't equal 0. If it equals 0, splat. Orange soda, orange juice, everywhere. Let's do that. So if we add the 2.5 times 10 over, you would end up with 25. 2.5 times v squared equals 25. Greater than that, you divide by 2.5 and you get back to 10. So v squared is equal to 10. That means the velocity would be equal to the square root of 10. Square root of 10, which is 3.16. And again, I'm using 10 meters per second for gravity. 10 meters per second for gravity. Okay, we got a little bit more to go over, and then one last problem. So one of the main things that you need to be aware of is the normal force in relationship to gravity. And the normal force is always going to be going inward. So everything I'm drawing right here is the normal force. It is always going to be going inward, just like the centripetal acceleration. So it's going to be going inward. All right, so the normal force is essentially the centripetal acceleration in a way. All right, with that in mind, gravity will always point down. No matter what, gravity is going to point down. Normal force will always point inward. One last one before we call it quits. We got a 40 kilogram student. A 40 kilogram student is going to be riding a loop-de-loop roller coaster. When the car is at the top of the loop and is traveling 14 meters per second, the car exerted a downward force of 100 newtons on the student. What is the radius of the loop? So we're just using the same idea that we had before. And that idea would be that we could take the tension is equal to mv squared over r minus mg again. Okay, but this time, instead of finding the exact stuff that we had before, we can plug in the tension. We know that downward force, that tensiony force, is 100 newtons. Would be equal to, the mass is 40, the velocity is 14 squared, divided by the radius, we're looking for the radius, and then minus 40 times 10. Okay, so with that in mind, we could continue to solve for r here. You could simplify a few things. Let's simplify a few things. Let's add this stuff. And multiply by, you know what, let's just add this stuff over to the 100 newtons. If we had 40 times 10, you would end up with 400 added to 100. So this is 400 added to 100 makes 500 newtons is equal to 40 times 14 squared over r. You could multiply by r and then divide by 500. And if we do that, if we multiply by 4 r and then divide by 500, you would end up with your radius is equal to 40 times 14 squared over 500 newtons. And when you do the math, 40 times 14 squared divided by 500, you end up with 15 0.7 meters. And that, ladies and gentlemen, is going to do it for this one. Until next time, everybody, stay positive, and I will see y'all later. Bye.